and then share my screen. Can you guys see the paper?
Yep.
Okay, cool. So today I'm going to be presenting a paper called Scaling Deep Learning for Materials Discovery. A lot of the, as I said before, just like a minute ago or so, a lot of the chemistry of this paper like was completely over my head. So unfortunately, I'm not really going to be able to get into the depths of that element of the paper, but hopefully I can at least give you guys a good explanation of the system that they used, because I actually think it's super cool and also really instructive. The system they use for material discovery. Just I wanted to talk a little bit about material discovery and then the specific focus of this paper. I watched this this YouTube channel called Real Engineering, and not like pretty consistently, and the um, the the presenter of that channel talks a lot about how like one of the leading things that leads to innovation in society is like materials. He doesn't always say it, but it's something that comes up every so often. Like I was thinking to myself, we even have like periods of human history that are described based on the material that was mainly used during that time, like the Iron Age and the Bronze Age. Like materials have like this have a massive impact on society, but it's one of these, I think, less sexy and less thought of parts of what makes our technology work. And then, so this paper is focused on the discovery of inorganic crystals. I wanted to, so there's some examples of inorganic crystals or things that are made from them are like semiconductors or carbon nanotubes. And I just found this this video from this guy that I wanted to post. It's just about like how carbon nanotubes could change the world. And so the question in the chat is, what's the name of the YouTube channel called again? Well, it's this is the channel, but yeah, it's a really good channel just for keeping up with some cool stuff that's happening in engineering or that happened in the past. But yeah, so these inorganic crystals can have like, if we can discover useful ones, like one of the main applications that they talk about in the paper is solid state batteries. Like if we could figure out how to make solid state batteries, which are batteries that where you can store energy within a material without having to use some kind of chemical reaction to discharge it. And they're made from solid materials as opposed to maybe liquids or gels. That could have like a massive impact on society, being able to find materials that could lead to solid state batteries. But there's so many different other applications. Before going into the ML, I looked, my first question when I was trying to understand like all of the chemistry behind this is like, what's a crystal? Maybe I've never really studied chemistry, but so if you look it up, a crystal is a material that has some kind of structure that's periodic. So what you can basically do is you can define some volume. I think it's called like the test unit or something like that. And within it, there's a structure. And then you can basically just tile this volume around itself infinitely to create the material. And so that's what a crystal is. And again, one thing that they pointed out in the Wikipedia page when I was reading about it is that the interesting, oh, there's someone who's running. The interesting thing about crystals is that they have they essentially like different structures in different directions repeating themselves. So like an example would be graphene, where in one direction you have like these very tight lattices, and in like the perpendicular direction you have essentially no chemical bonds and they're stuck together really loosely. And that's why like we can use graphene in pencils, because in one direction the graphene just like slides off of itself so you can draw with it. So this these differences in direction are what allow crystals to have like interesting properties. For example, another one that's cited in the Wikipedia page is that a specific type of crystals exhibit the piezoelectric effect, which is when you apply pressure to something, it creates an electrical current. So yeah, these crystals have these really interesting properties based on their structure that can be used in different applications, and I think that's why there's such a focus on them in this paper. And I really have to take my hat off to DeepMind because I feel that a lot of ML research that we see today, it focuses on the topic of generalization. So it's like, what's a method that we can apply to all these problems? Whereas you see DeepMind often taking like a very different approach where they say, okay, what's a really specific problem that if we could make headway in it, that it could be really powerful for the world. In this case, they chose the problem of materials discovery of inorganic crystals, or specifically like stable inorganic crystals. And they probably have like a big team of mixed, both like people who focus on ML and specifically deep learning, and then other people who are just really, really good chemists or focus on computational chemistry. And so they took this opposite approach where they're like, okay, we want to make headway in this specific scientific problem. How can we do that? And the solution that they came up with, I think, generalizes past this problem, but is super cool because they integrate so much domain knowledge into it. So that's a long introduction. In terms of what this paper achieves, they say it a lot in the introduction. So the goal of this paper is materials discovery. And specifically, they point out that at the time when this paper, this paper was published about a week or two ago. But this in this year, before the publication of this paper or before they made the code public for it, we had a database of approximately, if you look at all the data sets about this, 48,000 organic stable inorganic crystals. Inorganic stable crystals. And with the use of this method, they were able to add about another like 400,000. So they increased the data set by like almost 1,000% in terms of how big it was, in terms of how many stable crystals they were able to find. Not only that, but they were able to they've been working on this problem for about 2 years, and they have like something like 900 of the crystals. I think they say 736 of the crystals that they found were also experimentally independently verified that they existed. So there was ongoing research in this area because it's a big area, and so a lot of some of the crystals that they found, they've even there's other people who found them, which is a good validation that this method works, because as you'll see, it's completely done in simulation. There's no there's no lab in the loop that's actually verifying these materials exist. But it seems that the physics, like the physical chemistry behind these types of crystals has been studied enough that we actually have like good simulation engines for determining whether a specific crystal is stable or not. And so I think that's one of the main things that they take advantage of here. So let's dive into the paper a little bit more. Is there anything? I'll talk about some of the cool results besides the one I said before later. But let's talk about the overall approach. And I'll zoom in on this diagram here. So so I'm looking at at part A of this figure, and I think one of there's two machine learning components to this paper. One of them is the use of a graph neural network as the type of model that is used to that is used as part of the like as a step in this process of material discovery, and I'll go into how later. And the other one is active learning. So I've never really studied active learning, unfortunately, so I'm going to give you my understanding of it. If anyone has a better one or something they want to say to add some more detail, that would be great. But so my understanding of active learning is where you're you have like a data set, but you also have the ability to either collect more data, or the other application that I've seen it used for is that you might have like a massive amount of data, and you want to minimize the amount of data that you need to train your model on in order to make it as performant as possible and generalize as much as possible. So there, in the second case, you are like looking for candidates to add to your data set that create like as much diversity in terms of the data set such that the model generalizes. Here, this is definitely their approach is definitely one of active learning, but it's really only focused. It's not really focused on like maybe a more complex analysis of new candidates. It's only looking for new candidates. So it's saying like I want new data to put into my data set that wasn't there before. And so the way that this whole process works is, let's start on the left, is at a very high level, is so they start a round of active learning. And then what they do is that they have these two pipelines. Let's focus on the structural pipeline first, is that they'll choose some like structure, which is basically they'll choose some molecule that I guess is an inorganic stable crystal. And then they'll make structural changes to it to make it different from anything else in the data set. And they'll come up with like a massive set of candidates. I mean, like hundreds, thousands, maybe even like way more than that. I don't remember the exact order of magnitude. Then they transform it into a graph. So they're basically processing that candidate into a form that a GNN can process. And they put it through the GNN to estimate its stability. And then what they do is they threshold that estimate. They threshold the estimates to choose like a set of like good candidates to perform. I think this is density functional analysis or density function analysis. I think it's density function. Let me zoom out. It's. I should get this right. Yeah, density functional theory. So this is an analysis which provides like a pretty good, or I don't even know it. How do I get rid of this down there? Do that for now. This analysis provides like maybe, and it might even be like a complete proxy for whether this is a stable crystal or not. But so
yeah, I think it sort of tries to simulate or actually calculate how the electron clouds will distribute in your material, and because the energy of a material is essentially how the energy of the electrons are, how comfortably they sort of fit into this thing. They fit very comfortably. It's a stable material, and you can sort of approximate that with these fairly expensive calculations, right? Especially once you have large materials, it becomes quite intensive and smart to calculate these. It's not entirely trivial.
Yeah, they point that out later, and hopefully I've underlined that. But if not, they talk about like how the scaling of this analysis is just really bad as you increase the complexity of the crystal. And so then so they're using machine learning in terms of this forward pipeline that we're talking about, in terms of the GNN, just to find like a set of good guesses that they can put through density functional theory in order to find like ones that are actually stable crystals. And then they add these to their database. That's this data of crystals. And then they repeat the whole process over again. they have two different pipelines. This one, the structural pipeline, is based on taking like a molecule and making structural changes to it, and then putting it through the GNN. The other one, again, this is where my lack of knowledge of chemistry hurts my presentation, is supposedly another way of representing a molecules in terms of the ratio of elements or something along those lines. And so you can define a graph based on that, and then you can use the GNN to determine stability, and then basically do the whole thing, but looking at the molecule as a composition of elements as opposed to as like a structure or like of like bonds between atoms.
Yeah, I think that sort of has to do with the fact that certain a crystal is a structure, right? But it's also the composition. And what can happen is if you think of something like tin pest, you can have like a stable crystal. However, over time it can form into an even more stable version of that. And so even though while something is principally stable, it doesn't mean that it is stable long term, because it might very slowly, but sometimes also quite rapidly, move into another crystal form that might already be known, or might be even more stable.
Yeah, I'm glad you're here, Arvid, so you can add some actual detail to this. But
I don't have a good knowledge of this stuff either, right? It's just
but it's good to know this stuff and to be able to add this detail. So they have these like two different pipelines, which I think are based on the fact that there's these two different approaches, maybe in the literature, for how to generate new candidates. And they perform this active learning pipeline 6 times, and they generate 2.2 million stable structures. But I think they're only able to verify that like around 400,000 of them are actually stable. I'll get to a little. I'll try to add a little bit more detail to that, like why 2.2 million went to 400,000 later. But there's some in terms of this process, which I hope I've explained well, of like doing active learning. There's some things I want to add to it to point out like why this approach is, I think, really cool, and also why it's even necessary. So they're trying to generate new materials, and this is a process. Like when you're trying to, the number of candidate new crystals that exist is massive. Like it's combinatorially massive. It's so large that a random search is just not an efficient way of doing this. And that's been the bottleneck that's existed for a really long time. And so what ends up happened in the past is that in order to come up with new candidate crystals, you'd have to have like experience as a chemist, and you would like see what crystals existed and why they were stable, and then you might think like, well, what if we make this perturbation to this molecule? Probably it will still be stable. And so then you'll do some experiment or put it through density field theory, functional theory, and you'll get a new material. But here they're actually able to automate the process of finding good candidates. So first, what they do is they take these two different approaches, like a structural approach where you perturb like existing candidates that you have, or a compositional approach, and you generate like a massive number of candidates. And then you use this GNN to really filter that down to a good set of candidates. And then you perform density functional theory on top of that. So it's basically taking a search problem that without any additional structure is just like way too large to make any progress in a meaningful amount of like in a small enough amount of time, and finding these ways to make it into a search problem that leads to getting new good candidates very quickly. And they say that so when they started doing active learning, the structural pipeline, about 4% of its candidates would lead to of like candidates that were chosen from it would lead to stable crystals or stable structures. And then for the compositional pipeline, about 3%. And by the time that they had finished the 6th iteration of active learning, after the pipeline with the GNN in the loop, like the output of the GNN, about 80% of the candidates were structurally stable. I mean, sorry, were stable structures. And then for the compositional pipeline, I think it was actually only 33, but still that's a massive increase. So they found a way to use deep learning and GNNs to make this search way, way more effective. And that's what allowed them to discover so many new materials. And that's really the genius, I think, of this approach. The other element of it, I think, is that if you couldn't use a computer to calculate to do the analysis that was being done with density functional theory, then you couldn't use this approach. So there's also an element of the fact that we have a good enough simulation of this system, essentially, that we can use the simulation as a proxy for the real world and get a lot of good results. So those are kind of the constraints the things that we have here that they've taken advantage of from the domain are like, one, these two different types of pipelines and the prior work in these areas of generating candidates based on structure and composition, and then two, being able to do density functional theory without any humans in the loop, and then the main thing that the main contributions are using active learning to create GNNs that are really effective at filtering out unstable structures. And so you can see here, the number in figure B, you can see that this is a number of new materials that they've contributed to the total database of stable structures. Here are some of the structures that the new crystals that they've identified in C. And then what else do they show? Yeah, they show you the precision of stable prediction. And the last one is just the mean absolute error in terms of calculating the energy within these crystals, which is the main thing you need to be able to calculate to figure out if they're stable, with the training set size as it increased. So yeah, overall, really cool. I'll add a little bit more detail about the method. Ooh, there we go. Let's see. I just want to talk about what GNN is being used and some other stuff. Okay. Yeah, I'm not going to talk about that. They use two different methods. I guess I'll just say they use two different methods to generate a set of new structural candidates. I would go into the method section, which is after the conclusion, if you're interested. In my opinion, as someone who's not in the field, it just shows how smart they were in terms of their use of domain knowledge, or the value of working with someone who has domain knowledge when you're trying to make progress. I don't think that ML and as someone in machine learning should view problems as black box with respect to the domain. But so the one thing I found interesting is, so they call their model GNOME, and it's a GNN, a graph neural network that predicts the total energy of a crystal. And they actually use a really simple GNN as their neural network architecture. It's one of the first GNNs that was ever suggested, and I think it was suggested something like 6 or 7 years ago. So I don't even think that well, I just find that interesting, because if you look at the literature on what are the most performant GNN architectures, this one isn't even mentioned anywhere. But then it was good enough for this application, so they just used it. So yeah, I guess my takeaway from that is something along the lines of that the focus on augmenting the data set must have been so much more important than any kind of architecture innovation that they don't even really, I don't even know if they tried other architectures, but this one worked and they focused on the data instead. So yeah, they use a really simple and old GNN for the paper. Yeah, here's where I talk about the hit rate. I talked about that already. And then, okay, yeah, that's basically the method. I don't really have anything else to point out. They talk about how the after they introduce active learning here in this section, they're basically just talking about results. So they point out that like the test loss performance of GNOME models exhibits improvement as a power law with further data. So like it just increases with a power law with respect to the amount of data you have. And sorry, yeah, I won't say anything about that. Okay, so if you look over here, they claim to have created a data set of 2.2 million stable structures. But then if you look at the results over here, discovered stable structures, they say GNOME found 2.2 million structures with respect to the materials project. Of these, 381,000 entries live on the updated convex hull as newly discovered materials. So I think I've read like 10 pages from a book on convex optimization and like convex functions and stuff like that. But a convex hull is essentially like a volume where you can draw a line from one at like any point within the volumes to another point within the volume. And so it seems like maybe there's a convex hull which describes a set of stable materials. And so if you find a new stable material that's within that convex hull, then you know that it's stable even without testing it experimentally. That's my guess of what this means. But that's why they only have 381,000 entries as discovered materials instead of 2.2, because they live on the updated convex hull, as opposed to, I guess the other ones are outside of it. It'd be interesting if we had a chemist and asked them like, so what does that mean, that the other ones aren't stable, or that they define a new convex hull? Is that a big deal that we found materials outside of the convex hull? I'd be interested to hear what they have to say.
I'm not sure, but I think that is exactly this phenomenon that you can have stable crystals, but if there's like a competing stable crystal that is ever so slightly more stable, there's a chance that it would essentially move over. And so it's and sometimes because these ended because especially if you have a very large structures with sort of, as you said, like loosely tied layers, sometimes moving between different states is actually not that expensive if they are energetically very close, and then but look stable might not be. I think one example I can put in the chat is quite cool, because you have a picture of how the same chemical formula can have different crystal structures, which are fundamentally very, very, very different beasts altogether.
Yeah, they even say something along that here, where like GNOME displaces at least 5,000 stable materials from the materials project and this other data set. So it's probably
something even more stable than what was currently thought the most stable. Yeah.
Wow.
It's pretty cool.
Yeah, it's so cool. Okay, so they've talked about the number of materials that they've discovered, and then they talk about some like downstream applications for it. So composition families of interest is one. So they talk about. I'm just going to read out this part so you can see what I'm talking about. So they find there's different applications of these stable crystals, and they're basically saying we found a ton of new candidates that people like people could use or try out for different things. So like first off, layered materials are promising systems for electronics and energy storage methods. Methods from previous studies suggested 1,000 layered materials are stable compared with the materials project, whereas this number increases to 52,000. So they've have 52,000 new materials. Similarly, following a holistic screening approach with filters such as exclusion of transition metals or lithium fraction, we find 528 promising lithium-ion conductors among known materials. So essentially, they find within these 381,000 materials, they find a ton that are useful in like very specific applications that we want to use them for, which I just think is super cool. I was even wondering to myself, like, I wonder if anyone's going to get their PhD based off of the fact that we've increased the pool of materials, and also downstream, like whether one of the pool of materials that they've discovered, one of the materials in this pool is actually going to lead to solid state batteries. That'd be such a huge contribution to our society if we could do something like that. So super cool. Then they point out a couple of other things. I'm sorry about this, but like again, my understanding of chemistry doesn't lend itself to this. But basically, what they talk about is I'll do this one first because I understand this one better. Is that they can use GNOME as a pre-trained model that they train further to simulate material, like essentially like atom and ion and electron dynamics in a material, so material dynamics. And so they basically show that they can that they can pre-train this model, and it does a lot better than a model that isn't pre-trained, and specifically at the case of generalization. And they point out that most previous models that tried to simulate material dynamics, the way it works is that you have to collect data about that material, and then you train a specific model for it in order to use it, the model to predict materials dynamics. Whereas here they have like pretty good zero-shot scaling and generalization by using this pre-trained GNOME model that they use to calculate like the energy of a material. So like they train the model at 400K and then they test it at 1,000K, like in terms of temperature, and they see really good performance there. So not only in terms of discovering this is a contribution not only in terms of discovering new materials, but also in terms of being able to like better model how these materials will interact at different temperatures and in different conditions. They have a specific part about like screening for solid state batteries, which is just over here. And then yeah, this is also about modeling, I think what you would call molecule dynamics. It's about just basically they're able to train a really good model for modeling interatomic potentials as well. So yeah, this is a contribution both in terms of material discovery and in terms of like basically modeling computational chemistry. Is there anything else I want to add? I knew this one was going to be a little bit short because I didn't really understand the chemistry part of this, and there's so much chemistry. But and I guess the last thing that I wanted to point out is when they're using GNOME, they actually use an ensemble instead of just using a single. So they're using a GNN architecture, but they're using an ensemble, and they use 10. But again, I was like, I think it's so interesting how they're using such simple techniques. If uncertainty quantification is like such a massive part, a field of deep learning, and there's so many different methods here, but they're like, okay, we'll just use ensembles, we'll average the outputs, and that's how we'll do it. And then they have a little bit of a heuristic at the end for making the uncertainty quantification better. But yeah, real use of really simple ML, and just using some domain knowledge to make it really powerful. So that's really all I have to say. I'm happy to try to answer any questions that anyone has. But I hope I've given a color of like what's the system they used, why they could use it, and like what are the results of it. Cool. If no one has any questions, then I'd say let's just finish early. I hope you guys found this paper as cool as I did. I was like, I hope that I can work on a project that like this one day. Let me stop.
Thank you very much. It was very cool.
Yeah. Yeah, if there's a, Julian, do you have a question?
Yeah, I did put it in the chat there. It may be completely left field, but, and I realize this is about, can you hear me all right, by the way?
Yeah, yeah.
Okay. I realize this is about crystalline structure and so forth, but does it say anything about, or can you imagine anything about medical uses, drugs, organic materials to go in the body, etc.?
Yeah, so they have another model called AlphaFold, which is I think
right.
which is
The
focused
Google
on,
one.
Yeah, it's out of DeepMind as well. So it's their model. That I think focuses on organic materials because it's
okay.
It's about it models protein-protein interactions, and that seems to be like the main thing that determines like the effectiveness of a drug or something else in our body.
Yeah.
And that one's really cool. That actually my favorite outcome so far of people using AlphaFold, because there's actually a lot of companies that have spun out of DeepMind or are using AlphaFold but haven't spun out of DeepMind that use it. Is there was some researchers in like Texas who found that the saliva of like some kind of fly or something decomposes plastic, and then they used AlphaFold to find a material they could manufacture or could manufacture that does the same thing. Not a material, a chemical that does the same thing. So they were able to basically to artificially create a chemical that decomposes plastic, and that was thanks to AlphaFold in part, and also like the great research that they did. But I just think that there's a lot of cool stuff going on with AlphaFold, and I'm sure with this now that it's out there as well.
Yeah. I mean, the thing about the battery storage is and the solid state is one of the biggest problems we've got. Without solving that, I think we're going to have a lot of problems with the renewable transition. I can't see any way around it. I mean, we need grid scale storage of something that's cheap. It could be heavy, it doesn't matter, but it's got to be cheap and easy, and it hasn't got to be some really difficult rare earth that only the Chinese control. And I keep a gentle eye on that. I'm not completely immersed in it, but it is relevant to my energy work. I'm writing a book on natural gas. But yeah, without grid scale batteries, so this could be hopeful.
I think there's also, for speaking of organic stuff, the crystal structure I think can be quite important for bioabsorption properties. I think you can take the same chemical, but say take aspirin, but the way it is put into a tablet form and how it interacts with your I don't know what they're called, mucus slime cells, is I think determined by how porous it is, right? So if you have something that is naturally more porous than something that is very, very densely packed, you can get the same effect with much lower dosages, which is
interesting. Yeah, that could be really good. Yeah. Oh yeah. Well, really interesting paper. Thank you, Peter.
Thank you.
Yeah. Great. Well, thanks everyone for coming, and we'll see you next week.
Bye-bye.
Thanks, Peter.
Bye.
Thanks.